Swayam Prabha. Digital India. Educated India.
So, welcome back. We have been looking at games. We started by looking at game theory and observed that these are models of rational behavior in multi-agent environments. And then we narrowed down our focus to board games, which are 2-person zero sum complete information alternate move games, deterministic games. And we looked at how there is a notion of a minimax value for such games and how to compute that value. We also made an observation that real games like chess and Go are too large to be analyzed completely, as a consequence of which we do not know what is the minimax value of a game like chess. But if you want to write programs to play those games, then we have to adopt some approaches where you do not have to analyze the complete game tree, and we do that by doing a finite look ahead. So, let us start on that process and see how we can tackle real games without having to wait for eternity till we have analyzed the game. The main problem is that there is exponential growth, that each player has a certain number of choices, and at the next level the next player has that many choices for each move made by the first player. And in that sense, as we have already seen in other situations also, the game tree grows exponentially. So, supposing there was a simple game in which each player had 4 choices. So, the branching factor of the tree is 4, then a 3-ply look ahead search tree would inspect 64 nodes. At the next level there would be 256, after that 1024 and 4096. Now, these are trees which we obviously cannot draw on these pages, and also we cannot analyze them if they are long games. Long games meaning the number of moves that a game has, and most games, as we have observed, have higher branching factors. So, let us go back to what we said about chess. We said that the total possible games is about 35 raised to 50, which translates to 10 raised to 120, and we said that 10 raised to 120 is a number that we cannot even comprehend. Our human cognition is attuned to the world around us, and numbers like 10 raised to 120 do not make too much sense. So, let us assume that we had a very powerful machine that could inspect a trillion leaves a second, that is 10 raised to 12 leaves a second, and as you can see that such a machine would require 10 raised to 108 seconds. So, all you have done is from 120 you have subtracted 12 and you have got 10 raised to 108, and it would require 10 raised to 108 seconds. So, since we are working in powers of 10, we will assume that our calculations are all powers of 10. So, we will assume that a second has 100, a minute has 100 seconds, and an hour has 100 minutes, and so on, just to take a more conservative approach and see how long it would take for us to compute or analyze the complete chess tree. So, if we had 100 seconds in a minute, then this time would reduce to 106 minutes, and if we had 100 minutes to an hour, this time would reduce to 110 raised to 104 hours. If we had 100 hours in a day, this would become 10 raised to 102 hours, and if we had 1000 days in a year, this would become 10 raised to 99 years, which is 10 raised to 97 centuries. So, obviously, this is a number still beyond our comprehension. So, let us assume that, compare it to the size of the universe, for example, and it is estimated that the universe has about 10 raised to 75 or 10 raised to 80 fundamental particles, and if each of them were to be a supercomputer which could inspect a trillion leaves in a second, then what would happen? So, what we are saying here is that if every particle in the universe was such a computer, then the total number of games we have already said is 10 raised to 120, and if we had 10 raised to 75 machines and each could inspect 10 raised to 12 leaves a second, it would still require 10 raised to 33 seconds. And then we go through our similar calculation as we did recently. If we had 100 seconds in a minute, it would need 10 raised to 31 minutes. If we had 100 minutes in an hour, it would need 10 raised to 29 hours. If we had 100 hours in a day, it would need 10 raised to 27 days, and if we had 1000 days in a year, it would be 10 raised to 25 years, 10 raised to 24 years, and which is equivalent to 10 raised to 22 centuries. So, again it is 10 raised to 22, that is 1 followed by 22 zeros, and that is not the kind of time in terms of centuries that we are willing to wait. So, what do we do? All game playing programs do is they do a limited look ahead. So, if this is a game tree which is going exponentially, we do a look ahead which is called a k ply look ahead. So, a ply is a name that we use commonly in game playing parlance. We say how many moves are we playing. So, k ply look ahead means that you are looking at k moves. You make a move, your opponent makes a move, you make a move, and so on, and you are only looking up to k moves ahead. So, for example, if you are doing a 4 ply look ahead, then we are looking at part of the game tree and not looking at the complete game tree. So, what do we do at the end of these 4 plies, which is called the horizon? We have reached some board position, but the board position is not a completed game. So, we do not have the outcome of the game, we do not know whether max is winning or max is drawing or max is losing. So, instead we do what we often do in AI, which is to apply some sort of a estimating function or a heuristic function, and for any board position on the horizon, we estimate the value of value h, and we will use the term h for this value, carried forward from the idea of a heuristic function in search, and we estimate this value h by applying a evaluation function. And after we have applied the evaluation function, we back up. So, we have applied the evaluation function to all the nodes in the on the horizon. So, I have not drawn all of them, but you can imagine that at all the nodes you apply the evaluation function, and then you back them up, and based on the backed up value, max decides what is the move to be made. So, how does game playing work? The basic idea of game playing is not to analyze the whole tree in one shot, but to do this every time you want to make a move. So, the high level algorithm for playing a game for max, and we have said that we will always look at things from the perspective of max, is that while the game is not over, you call your k ply search algorithm, which will look ahead up to k plies, apply the evaluation function, back up the values and choose the best move. Based on that you make your move, and then you wait for min's move. Min is your opponent, and when min makes a move, then you again call for k ply search. So, the game playing proceeds as follows. So, this larger envelope that we see is the game tree, but we are not going to explore the entire game tree by any means. We are going to explore small portions of it up to a finite look ahead, and first we, as we have just observed, call k ply search, and based on that k ply search we make one move. Okay. After having made this move, we wait for your opponent to make the move, and very often people try to figure out what to do in this time when you are waiting for opponent's move, but we will see, we may get back to this a little bit later. But so, this is the first cycle that of this game playing which is over, which is that you have made a move after doing k ply search, and the opponent has made a move by whatever means the opponent is adopting, and now again you have to make a move. Now, obviously, this is a node that you have seen earlier in your k ply search, but now you want to again look at k plies ahead from this particular position. So, what do? You do a secondary second search, you again do k ply search from here, you again make your move, you again wait for your opponent moves, and then when you have to move again, then you again call k ply search. So, in this manner, for every move that you make, you will call k ply search, and in some sense you will look that much ahead. So, 2 moves ahead in every search. So, in the first move in the first search you made a move, opponent made a move, then when you do again k ply, that means you are looking 2 more moves ahead, and in that sense you keep looking further and further into the game, and hopefully far enough so that you get a good sense of where the game is going essentially. What should k be? Now, k typically depends on the computing resources that you have, and also the time that you have for playing the game essentially. Now, if you are writing a chess playing program that was playing in a tournament, then you are allotted a limited number of time to make a certain number of moves, and based on that you would make you would decide how much should the k ply be essentially. So, what is this evaluation function that we are talking about? How do we, what does it do for it? It is exactly like a heuristic function that we saw in heuristic search, that it is a static function, and by a static function we mean that it only looks at a board position and does not do any look ahead or search from there, like the heuristic function that we had in our heuristic search algorithm. So, it looks at a board position and returns a value in some range, which we will call as minus large to plus large. So, this minus large is an approximation we use when we are writing algorithm to say that it can be as small as possible, and plus large means that as large as possible essentially. So, that will obviously depend upon your design of your program. This minus large to plus large interval is just a convenient scaling up of the interval minus 1 to plus 1, the real interval which we are interested in, which converts the set of 3 outcomes in the game, which is minus 1, 0 and plus 1. Remember, minus 1 is a loss for max, 0 is a draw for both players, and plus 1 is a win for max. So, these are the 3 possible outcomes, but now we are having our evaluation function return a value in the range minus 1 to plus 1. Plus 1 is still a win for max and minus 1 for min as before. So, these are the extremes of our interval, but in between any values, positive values are good for max and negative values are good for min, and typically the evaluation function is computed by adding up features, capturing material strength along with features which represent positional strength. So, this text has gone a little bit out of the slide, but the last line should reach along features representing positional values essentially. So, let us look at some of them. Let us consider a simple game, the tic tac toe game which children play, also known as cross and knots, where alternately you put a cross or a knot meaning a 0 on one of the 9 squares that are available to you. So, this is a starting position in which the first player max has to move, and max has to decide where to put a cross. So, that is a task that max is addressing. So, let us assume that max is doing 2 ply look ahead, which means that max is looking ahead 2 moves, and so first max considers whether to put a cross at the corner of the game, corner of the board, and that is the first move that max is considering, and then for this move that max is considering, it considers all possible moves that min can make. So, min is putting a knot or a circle on the board, and we have just drawn all the distinct positions at which min can play the knot. In practice, of course, there are 8 possible positions in which min can play a knot, but some of them are symmetric with respect to each other. So, for example, in the second board position, if min were to play a knot here, then the 2 positions are strategically identical. So, we kind of somehow ignore symmetries in our analysis, though when we are writing a program we may or may not ignore symmetries. So, in any case there are these 5 distinct moves that min can respond to by in response to max's first move, which is let us call it the node A essentially. So, in response to A, min can make any of these 5 choices, and since max is doing a 2 ply look ahead, at this stage max applies a evaluation function, and let the evaluation function be as follows, that the evaluation function counts the number of free rows or columns or diagonals which are available for max, and from that you subtract the number of free rows, columns and diagonals available for min. Remember that the game of cross and knots is one when someone gets 3 in a row or 3 in a column or 3 in a diagonal. So, we are just trying to see how much is the possibility for each of these 2 players. So, let us look at a value for the last board position. In the last board position, we have max has played at the corner and min has played at the center. So, if you look at this board position based on the evaluation function that we have, then you can see that these are the following possibilities for the 2 players. For max, we have shown in red that there are 4 possible rows or columns or diagonals available where max could possibly win a game, but for min we have 5 of them. So, those 5 green lines that you see on the rightmost this thing, they represent the 5 possibilities for min. So, the evaluation function for max for this node evaluates to 4 minus 5, which is minus 1 essentially. So, in this manner we keep applying the evaluation function to each of those 5 board positions on the horizon, and then we know that we are doing a minimax backup rule. So, the best value or the best value from min's perspective, which is the lowest value amongst these 5 values. These values are 1, 0, 1, 0, minus 1. So, since A is a min node, min would choose the smallest of these, and therefore, this value would be backed up for the node A, and we would back up the value of node A as minus 1. Okay. So, this illustrates the evaluation function for the simple game of tic tac toe. Let us now look at perhaps the most possible game that has been used in for programming, which is chess, and this depicts a simple evaluation function for chess. This evaluation function has been attributed to Claude Shannon, who was one of the pioneers of computing, known as the father of information theory. And this evaluation function, which he called as f of p, a function of a position p, is made up of a set of components essentially, and the components are as follows, that the letters k, q, r, b, n, p, they count the number of kings, queens, rooks, bishops, knights and pawns that each player has. K is for max and k prime is for min essentially. So, obviously, in the case of king and queen, at least in the beginning of the game we have only one queen. Towards the end of the game you may have 2 queens if a pawn gets promoted to a queen, but in the beginning you may have one extra queen. If you have if both of you have a queen on the table, then it amounts to equal. So, q minus q prime would be 0, but if one of you did not have a queen, then it would add up to the evaluation function. The numbers that you see that you are multiplying these differences with 200, 9, 5, 3, 1 and so on, these are the weights that you assign to each piece essentially. So, many chess players would say that a rook has a weight of 5 on some scale, on which queen has a weight of 9, the bishop and the knights have weights of 3, pawn has a weight of 1 and so on. So, apart from material value, we also have positional value, as we have said, and the positional value here is indicated by these 3 features D, S and I, which talks about how the pawns are organized, double pawns or blocked pawns or isolated pawns, and M is the mobility, the number of legal moves that are available to each. So, the more moves you have, the more the choices that you can make and the less constrained that you are. And these mobility features, which have not been listed here completely, have things like king safety, central control of center, pawn structure, king tropism, double rooks and so on. And you can devise more and more such patterns or features to evaluate the board position of a game. And the program Deep Blue, which was a program which beat Kasparov in 1997, has about 8,000 such components, 8,000 different such components, and this is according to the paper that was published by the author of the program, one of the authors of the program, Campbell, in 2002. Let us look at what else you can do in chess. So, we said that positional features are important. So, essentially, how do strong chess players look at a board position and say, oh, this is good for max or good for white or this is not so good for white and things like that. The positional features are concerned with mobility, board control, development, pawn formations, piece combinations, king protection, etc. So, some of the features that chess players or chess programmers have used are as follows. For example, that two rooks in the same column have added value, because the rooks can move either vertically or horizontally, and if they are in the same column, that means they are protecting each other. So, the other rook can kind of freely move up and down. A pair of bishops is better than a bishop of a knight. So, those of you who have tried to do end games would observe that this is the case, that with two bishops you can checkmate an opponent, but with a bishop and knight you cannot. Knights are valuable in certain kinds of end positions, and pieces must become mobile and either occupy the center or control it. So, center control has been a very focused point for chess players. So, chess enthusiasts very often they start off by looking up a book like Modern Chess Openings, which describes the result of analysis by hundreds of strong players as to what are the ways to start opening up the game. So, we had observed that max has 20 moves to start with in chess, but very rarely would more than 4 or 5 of these 20 moves be used by any good player. That is because the cumulative experience of chess players has resulted in the knowledge that certain moves are good, and the focus of such things has often been to control the center. So, because center is where the maximum action can take place. So, if you want to control the center, your pieces must be either occupying the center or they must be controlling the center remotely. So, for example, a bishop can be attacking some center squares or a knight or a queen and so on. Control of center has been a very strong focus point essentially. Then chain pawns that support each other are better than isolated pawns, because the opponent cannot just freely grab a piece that you have on the board. Pawns in the same column or opposing pawns head to head are not good, because their mobility is reduced. Pawns heading for promotion have added value. So, if you remember the rules of the game chess, which we have not discussed, but I hope you know them, that if a pawn reaches the last square, the last row in the chess, then it can get promoted to any piece that the player chooses. Most often it is the queen, but in some peculiar cases it may not be the queen and something else. The king needs protection in opening and middle games. So, a focus of chess openings is to first somehow secure the position of your king, and there are various kinds of strategies that people use, like castling for example, and these give high value to board positions. But in the end game, when the number of pieces are small, the king may be an offensive piece and it has a different value essentially. So, a constrained king may not be good, but a freely moving king may be good essentially. Things like pins, forks, discovered attacks are also considered while computing positional value essentially. We will look at forks in a moment. One question that you might ask is, if you have an evaluation function, why do you need to do look ahead at all? Why not just do one ply search, as this diagram shows, that max considers all the possible moves that max can make, applies the evaluation function to each of these moves and chooses the best one. Okay. Now, this would require that your evaluation function is very good essentially. Now, the chess psychologist de Groot had done a study in which he had observed that grandmasters store tens and thousands of chess, what he called as schemata. So, these are patterns which they have kind of learned through experience, and simply by looking at a chess position, a grandmaster can say this is good, this is not good, and so on. And the way they do it is because they have accumulated their experience of chess or knowledge of chess into schemas or schematas, which they can spot immediately essentially. So, there is always a trade off between how much you can recognize by looking at a board position versus how much do you need to kind of look ahead and try to figure out what is going to happen essentially. The trouble is that it is difficult to devise an evaluation function that is good enough to play with one ply look ahead essentially. We rely on a combination of evaluation and look ahead therefore essentially. So, let us look at some situations where what we are doing by evaluation could have been got by look ahead. Here is a fork as it is called in the game of chess. So, it is a fork because the black knight can is attacking both the white queen and the white rook. And if you have a pattern which says that you give certain value to fork, if you can see a fork like this, then it actually gives us some information which further search would have revealed essentially. So, in this pattern, as we said, the black knight is simultaneously attacking two white pieces, the queen and the fork. Now, if you remember, we briefly mentioned what the valuations of these pieces are. The queen was 9 points, the rook was 5 points, and the knight was only 3 points. So, if the knight could, if the black player could exchange the knight with the rook, then black player would happily do that, because it would give the black player material advantage. The white player can only move away one of the two pieces. So, that is why it is called a fork, that white has limited choice, which is to either move away the queen or move away the rook essentially. Now, this could have been discovered by further look ahead. If you had done a little bit of look ahead, that white plays the queen somewhere, and then the black knight captures the rook, and somebody captures the black knight, and then therefore, this is the final material position. But remember that the evaluation function is applied on the horizon. The horizon is a place where look ahead has stopped. So, if you can catch that pattern at the horizon itself, that means you have got something extra from looking at the board position, which you would have otherwise got if you had the freedom to look ahead further essentially. Some very popular chess positions are called Zugzwang. So, the Zugzwang is a German word. It is used in chess and in other games also, where one player is put as a disadvantage, because they must make a move when they would prefer to pass or not move. So, we will not discuss this in too much detail here, but if you look at this chess position shown here, then you can see that white has got 2 pawns and a king, black has got 1 pawn and a king. If somehow white could move forward and promote one of his pawns to a queen or something, then white would eventually win the game. But the situation is such that black is preventing white from coming forward essentially. So, a player is said to be in zigzag when any possible move will worsen the position. Now, in this board position, what is really critical is whether it is white to move or whether it is black to move essentially. Now, if white is to move, then black is safe, because the only thing that white can do is to move the king somewhere, and black can also do some shadow moves and keep coming back to the same position. White cannot move the pawn, because the pawn would be captured by the black pawn, and then if white moves the other pawn ahead, the black king can go after it and capture it essentially. So, if white is to move, then black is safe, but if black is to move, then the only move that black can make is to move the king. Then if black moves the king, then white will be able to capture the black pawn and eventually win the game essentially. So, sometimes in the evaluation function we also include the fact as to whose turn it is to move essentially, and many chess programs do that. Let us look at another slightly more sophisticated zugzwang position. The position is similar in the sense that the black king is trying to protect 3 pawns and the white king is trying to attack one of those pawns, so that white can go ahead and promote a pawn. The material strength is equal, but the positional strength is different, as you can see. Now, in this position black is again at a disadvantage if black were to move. If white is to move, black is safe, because white cannot attack any black pawn essentially. White, so again the king would have to retreat and black could mirror the move or something like that. But if black, so if white were to push the pawn, it would get captured and that would be the end of the story for white essentially. But if black is to move, then black is forced to withdraw protection from one of the 3 pawns, and then again white would go ahead and capture that pawn, clearing the way for some of his pawns to advancing and becoming a queen. So, again this kind of a position is critical to as to who has to move essentially. Let us look at one more position, and here we want to illustrate that because of the fact that you are doing a finite look ahead, you can sometimes not come to the right conclusion, and this is simply because you are doing a finite look ahead. Now, this is a very contrived chess position. It was created specifically to test computer programs, and this position is known as the poisoned rook. So, if you look at this position carefully, you will see that there is a kind of a fortress in which white is living of black pawns, and none of the white pawns, and none of the black pieces can penetrate this safe area that white has. But now black has very cleverly offered a rook as sacrifice to white. Now, if you were to simply go by material advantage, which is what chess programs do, then capturing a black rook would definitely be worth its effort, and that is what this program called Deep Thought 2, which could actually selectively look ahead up to 10 or 11 ply, capture the black rook and with the white pawn. Once that white pawn which captures the black rook is removed, it paves the way for other white pieces to come forward and eventually defeat other black pieces to come forward and defeat this thing. So, eventually Deep Freeze also went on to lose the game, but human players quickly realized that this very contrived structure, you would rarely have 8 pawns on each side in such end positions, but in this structure any human would recognize that all white has to do is to simply move around the king in its region, and there is nothing black can do to win the game. If black had a black bishop, then the black bishop could have possibly attacked one of the white pawns, either this one or this one or any of the white pawns, because they are all sitting on black squares, but black does not have a black bishop in this case. So, this illustrates that a finite amount of look ahead, in which you are looking at material value and positional value, is often unable to discern some odd situations like this, which human beings can still do quite well. Okay, so, in the next class we will start looking at how to analyze game trees with a finite look ahead. So, here we have a small game tree where each player has 2 choices at every stage, and we are doing a 4 ply look ahead, and at the bottom are the leaves to which the evaluation function has been applied. So, we will take this up in the next session.